So good evening, everyone. It's a pleasure to be here in Natal again. And really would like to thank the organizers for allowing me to present here. And I pretend to be very brief, okay? I'm sure that everyone is tired already. So I won't take too much of your time with my talk. So I'm gonna tell you about this property we call the shooting property of the quantum Ising model, or the transverse Ising model. And before I do that, I would like to make two remarks about spin systems, which may be obvious for a lot of people, but not to everyone, I guess. So let me start with that. So let us picture some spin system. That is a lattice of spins with some interactions between them. So I'm calling the lattice by lambda. And let's assume that it is in equilibrium. Okay? Its state is just the Gibbs state according to its Hamiltonian. And let's look at the reduced state of this global equilibrium state in some small region that I'm calling here X. So what happens is that, in general, this reduced equilibrium state is not an equilibrium state of that region. Okay? This is actually makes a lot of sense, since the global equilibrium state takes into account the interactions between the systems inside that region with systems outside that region, while the equilibrium state of that region alone doesn't take into account those interactions. So there is no reason why these two states here should be the same. Okay? So another remark quite related to this one is the following. So let's assume now that we have some perturbation in the Hamiltonian, which is restricted to some region on X. And we can then compare the equilibrium states of the global system with or without that perturbation. And what happens in general, of course, we should expect that in the spins where this perturbation is, you should observe some differences, right, between these two equilibrium states, since the Hamiltonian in that region is different. But actually, this perturbation can also affect the spins outside that region. Okay? So, let me give you a very simple example where these two things happen. So it's probably the most simple example we can see this happening. So let's take here the classical Ising model, right? So let's picture a chain of spins, and they interact along the z direction, right? You have an exchange coupling just in the z direction, and you have an applied field just at the first site. And it's quite easy. Well, you can do the calculations for the reduced state of the last spin of the chain, and you can explicitly see that, on the one hand, this reduced state depends on the field applied on the first site, and on the other hand, since in this case, the Hamiltonian of each individual spin is just 0. So the equilibrium state of that individual system should be just the maximally mixed state, since its Hamiltonian is 0. Okay? So, and on the other hand, this is quite intuitive, right? We expect that if the temperature of the whole system is not too high, if you apply a very strong field here, all spins should align due to that field, right? The second spin here will be likely to align with the first spin, the third spin should align with the second spin, and so on. So all the spins should be aligned due to the presence of this very strong field. So this is quite reasonable that we have this dependence here on this the site can be very far away from the first one, but its properties depend on what is going on with the first site. So what we can expect for the now quantum Ising model, or the transverse Ising model. By that, I'm saying that the Hamiltonian of the system, right? It's like that. You have an exchange coupling in one direction, but the field is applied in another direction. And I'm allowing here to have any kind of coupling, any kind of lattice in principle. Well, actually, I will explain a little better, but let's just focus first in the case of a one-dimensional lattice. But these couplings here can be anything, and you can have, in principle, every field in each site, except for some site L, where the applied field is 0. So if that holds, we can show that the reduced states at each side of the chain, divided by this site where the applied field is 0, is just the reduced state of that part of the chain alone. Okay? So this is why this is what we call the shielding property. So I will explain why the word shield appears here. And this was realized by Natalia Moller, and we wrote a paper on this jointly with Alberto Di Paolo. Anyway, so let me make a few observations about this result. First, notice that, okay, this is an exact result, okay? This is not an approximation or anything like that. It holds for any temperature for the whole chain. And so it is saying that, okay, if the field applied in this site here is 0, the reduced state of this part of the chain, okay, the sites to the right of that site, and the reduced states to the left of that site, they are the equilibrium states of just that part of the chain. Okay? In particular, the properties of one of the sides do not depend on the parameters of the Hamiltonian on the other side, as it was the case for the classical Ising model, right? Where the properties at the left, the most extreme side to the right is dependent on the parameters of the Hamiltonian in the first side. Okay? So the equilibrium state here behaves as if the right side of the chain, say, is shielded from the parameters of the left side of the chain, as long as this field here is 0. Okay? So you can have a very strong exchange coupling between these sides. You can have very strong applied fields to the left side of the chain, but the reduced state to the right of the site is completely independent on the parameters to the left side. So this is basically what we call that's why we call it the shielding property. But it's important to point out that this property may induce us to think that the global state just decoupled into two product states, right? You have the equilibrium states to the left of that side, and the equilibrium state to the right of that side, and the global state is just a product one. But this is not the case, okay? In general, these sides, each side of the chain, they may have correlations, and they will have correlations in general. Okay, just another observation. In that case, you also have a kind of dynamical shielding too, in the sense that if you take your chain in an equilibrium state, let's say the ground state, and so I'm here plotting this index here is representing the spins along a chain. This axis here I have time, and this color diagram is showing the magnetization of spins as a function of time and the particular site of the chain. So in this case here, this black line is along a spin where the interaction is, where the field is zero, okay? And at t equals 0, a perturbation is done in the first spin of the lattice, and this perturbation propagates along the chain. But you see that it reflects here as if these chains were decoupled, even though there is exchange coupling between the sides of each chain. So apparently there is no interaction between these two sides of the chain, but there is. But actually this dynamical shielding is just a consequence of a commutativity of the Hamiltonian in each side of the chain. This is something that is more easy to show and to prove that happens. It's actually a very simple calculation. But commutativity alone is not enough to show that similar property that holds for the equilibrium state of the global chain. We need something a little bit more smart to show that. But a simple way to see why this property holds is to use the so-called duality of the model. And this is a nice way to show for really a chain of spins. So it is well known that this model, the transversizing model, can be mapped into another chain of spins, and this chain is also described by a Hamiltonian of a transversizing model, but the holes of field and interaction exchange places. So you see here, if H is an applied field in your original chain, in this dual chain, we call it, it will be associated to an interaction between spins, while if this J here represents an interaction between spins of the first chain, of the original chain, it will be mapped in a term corresponding to a field in this dual chain. So if in the original chain, some site has no field, in the dual chain, you have a pair of sites which do not interact. So the dual chain will be really decoupled. They are just two independent Ising chains. But anyway, we can generalize this a little bit. So our lattice of spins can be a little bit more complicated as long as we have this kind of bottleneck. I mean, we have some spin, and this spin can interact with a lot of other spins to the left or to the right, and these spins can have very complicated pattern of interactions. But we can show that as long as the field is in this plane is 0, the same property holds. So in the equilibrium state for the whole lattice, you have the reduced states at each side of this lattice are independent from each other. In particular, they are the equilibrium states of that part alone. All right, so given that this holds, we then asked if in a configuration like that, the property would still be valid. I mean, let's say that I have some lattice of spins described by the transverse Ising model, and we can distinguish, let's say, a dividing surface of spins where the field is 0 at each one of them. So the surface divides the whole lattice in 3 parts. Okay, the surface itself and these 2 disjoint regions that I'm picturing here in blue and black. And we may ask ourselves if this property still holds here. And, well, actually it doesn't. And already for the most simple example we can think of, we see that the property is not valid. So in this very simple lattice with just 4 spins, and here with these edges I'm representing which one of them interact, has an exchange coupling interaction. And so if you make the field 0 here in these 2 sides, we would have such a situation, right? We have this surface dividing the lattice into 2 disjoint parts. The field is 0, but what we see is that, well, the reduced states in sites 1 and 4 are not just the equilibrium states of their own Hamiltonians, okay, in this case. Anyway, and in particular, we can see that the reduced state at site 4 can depend on the parameters we have for site 1. And we can see this quite explicitly. So in these plots here, I'm showing the magnetization at the 4th site as a function of, it's not readable here, but as a function of the field that's applied at the 1st site. So we have a quite explicit dependence. But the difference in these 4 plots here is the temperature of the global equilibrium state. So here we have a plot for very high temperature, and here at low temperature. And we saw in these plots that apparently, as we diminish the temperature, the property is close to hold, right? Actually, the scale here in this axis all these plots are very different. So what we see in this case, at very low temperature, the magnetization almost do not depend on the applied field in the 1st site. It seems that at temperature 0, the property still holds even in that case. So, and there is another example where we see that this property, strictly speaking, doesn't hold. And this is interesting because, well, this very simple lattice here, we can understand that, okay, these 2 sides are a surface dividing the lattice into 3 disjoint parts. And we can compute this and see that there is a dependence here of the reduced states in these sides with the parameters on the 1st side. However, we can also see this lattice as a one-dimensional lattice, and the result we have, the theorem we had, should work to show that the reduced state of this spin should not depend on the parameters that we have in this spin. since there is a site between them where the field is 0. So this is actually true. So this state, the state of this pin and this pin, they do not depend on the field of this site, but the joint state of these two spins do depend. I mean, just the correlations between these two spins depend on the field that is applied at the site. But each individual spin do not depend. So it's a quite neat and nice example. But anyway, we are in progress of really showing that this property is indeed valid, at least for the ground state of any lattice. But actually, it's not any lattice. So now we are assuming this more general situation, right? We can have a high-dimensional lattice with some dividing surface where the field there is 0. And we can show that the property holds. Okay, the reduced state in each of these regions is really independent of each other. They just depend on the parameters of those regions alone. But we need we are at a stage that we have to use some strained condition, basically for our proof to work and to get the result. And I will not get into much detail about this condition, but I mean, it works, and we can check at least for very simple and small lattices that the condition is valid. So I'm not so fast I was expecting. I don't have so much time. So I'm going to talk just a little bit about this condition. I'm about to conclude anyway. This is my last slide. And we need a sort of artificial condition. We have to assume that the ground space, I mean the subspace of least energy of the whole lattice, to be contained in some subspace where the spins of the surface are aligned in the following sense. We must have one configuration for the spins of the surface, and or the flipped version of that configuration. And if you take the whole subspace of the whole lattice, where the surface is in one of these two configurations, then we can show the result. We can prove the theorem. And, well, the closest thing we can find to that property is the property of being frustration-free. Well, actually, in general, a lattice described by the Ising model, quantum Ising model, will not be frustration-free. But where the sites have no field, if the model is frustration-free only on these sites of no field, then this would be actually a particular case of our condition here. Okay, so the closest thing we find to this condition we need is being frustration-free. I mean, in general, you demand frustration-free for the whole system, the whole lattice, and here we need frustration-free just in some region. And, well, that's basically it. I mean, we are still working on this generalization of the property, and I hope we finish this soon. And that's it. Thank you.
Oh, we have plenty of time for questions.